um, get started. Welcome everybody to the PSI seminar here on June 17th, 2026. We're pleased to welcome Dr. Jim Cutts, who has already had a stint with PSI quite a while ago, and we're pleased to have him here today to talk to us about volcanic activity detection on Venus from orbit and below the clouds. Thanks for being here, Jim. Take it away.
Okay, well, thank you, Amanda. Well, when I was with PSI, I left PSI as a Martian, doing most of my work on Mars. I'm coming back as a Venusian. Of course, I had a very rich set of publications on Mars science at the time. Most of the work on Venus has been on how we explore it with the technology and so forth. But this gets into a science topic that I got intrigued in a couple of years ago. So what I'm going to be talking about today, I'm going to be addressing a number of questions. First one is, what are the detection limits for orbital observation of near-infrared emission from volcanic eruptions on Venus? And then secondly, once we know those limits, what is the likelihood of them being exceeded by actual eruptions? Namely, and in this case, we'll look at Earth as an analog. Of course, if this is going to be interesting, we have to have a mission that can actually do that. So I'm going to talk about what form that might take. And then after recognizing that there are real limitations to what you can do from orbit, I've taken a look at what you can do about observing volcanoes if you can get below the clouds on Venus. Getting below the clouds on Venus isn't trivial. It's not as hot as the surface, but it's a little hotter than the upper levels of the atmosphere. And so we look at what technology is needed to make this possible. And then bringing this to a conclusion, I'm going to talk about how PSI is involved in pursuing long duration aerial exploration of Venus, both from the science and the technology aspect. So, kicking this off, the question of detecting volcanoes from orbit with nighttime near-infrared imaging was first addressed 25 years ago by Hashimoto and Imamura in Japan, who looked at what you could do with infrared nighttime imaging in the 1.02 micron window. Now, the key problem here is the clouds. And the clouds much more than the gaseous atmosphere because they scatter light. And they scatter light like a frosted glass mirror does. So light from the surface is diffused over an area roughly comparable in diameter to twice the height of the clouds. So this is around 120 kilometer radius, we think today, an area of about 10,000 kilometers squared. Now, they concluded that even with these considerations, hot lava emits much more radiation than the ambient surface. And so they concluded that a 1 kilometer squared lava lake at 1500 K, roughly 1200 C, could be visible, could be detected from orbit. If it was cooler than that, however, it would have to be very much bigger. But they didn't actually address the question of whether such large flows at such high temperatures were plausible. That's something I'm going to do. So what success have people had in doing this? Well, there were efforts using Venus Express data to detect such a thermal change. And there's one publication I'm aware of, and there were two observations, 113 days apart, which on Venus means you're roughly the same time of day. And you can see here the red splotch on the left has disappeared by the time you get to the right side. So there seems to be a change there. I've not looked at that paper in great detail, but there were a couple of other features that were talked about. But nobody else ever claimed to do the same thing with Venus Express data after that. And so that was really the only paper on that subject. On the other hand, much more recently, using measurements of actual topographic changes over an 8-month period, Herrick and Hensley reanalyzed some data from Magellan. I think it was in 1997, something like that. And they were able to see changes. Now, it should be said, the viewing angle of these radar images were different. So making detections of this kind, one is always a little bit skeptical, but their paper was published and is deemed pretty convincing by most people. So what else has been done? Well, as I said, no other surface changes from Venus expressed. There were changes in microwave emission reported from Magellan in 2010. Large areas were observed around 30 kilometers square. Changes were small. Akatsuki might have been a mission to do this, but I talked to Takehiko Sato about this 2 or 3 years ago, and he said, well, the problem was calibration. The calibration was never good enough that they could do this. And then there was another topographic change result reported in 2024. So there's quite a lot of observational evidence that something like this is happening. And then from a theoretical standpoint, a lot of people think that it's plausible that Venus, a planet of Earth-like dimensions, is still active. So what got me interested in this problem? Well, 3 or 4 years ago, maybe a little more than that, the Parker Solar Probe mission passed Venus and confirmed the existence of a significant new Venus atmospheric window below 0.8 micron. Now, the results I talked about earlier were all done in the window at 1.02, and they're saying there's actually a window below 0.8 microns. So I got interested in this, knowing that that would be favorable for reasons I'll discuss, and put together a poster paper in LPSC, and came to the conclusions that observations in this window could enable smaller flows to be detected than at 1.02 micron. So what is the evidence for this? For this window, at least. This is an image on the left, is a nighttime image of Venus in this whisper image, 0.4 to 0.8 micron. And on the right is a mirror image of Venus from radar data, and this is topography. And what you see is a correlation between the low signal in the dark area and the elevated area on Venus in red. And elevated on Venus means cooler, because the prime dictate of surface temperature on Venus is not albedo, but on the elevation of the surface. So, so this got me interested in whether we could use this window for looking at volcanoes in the same fashion that Hashimoto and Imamura had proposed, and Halligan had attempted to do. So why should this be better? Well, it's simply the shape of the Planck function. So what's plotted here is spectral radiance against wavelength for surfaces at several different temperatures. The one at the very bottom is the actual surface temperature of Venus, and it goes all the way up to 1600 C, which is hotter than any terrestrial flow has flowed recently, but is the temperature of flows that were experienced in the early history of the planet, so-called Komatiite lavas. But what I've looked at is 1200 C, which is typical of flows that we see in Hawaii and Iceland today. What you see here is that at 1 micron, the difference in radiance is about 4 orders of magnitude. And if you go down to 0.7 micron, it goes up to 6 orders of magnitude, a major advantage. So the question then is, are there any impediments to go into these low wavelengths? Well, the principal one's one that's obvious from the chart, that as you go to the lower wavelengths, the signal drops. So you're going to need longer and longer exposure times, and you're also going to be vulnerable to other sources of background. And one of these is the Venus aglow, and that's even visible in this image. You see that the image of Venus has this bright limb, and that's really the aglow that's looked at very long path lengths. And so we have to worry about that. So I took Hashimoto and Imamura's approach and added in the aglow and looked at what size of feature we'd be able to detect. And I discovered that, would you excuse me a second? I'm getting somebody calling me. That's you. I better give me a call. Yeah, I'm sorry. I'm back. So the optimal wavelength for very hot flows here is around 0.7. If the flows are not as hot, it goes to about 0.75. But you can see there's a significant advantage. And this is summarized in this chart, which compares the results at 1 micron with the Hashimoto and Imamura results. And so you see you get very, very similar numbers for where we actually had comparable data. And in the case of the 0.7 micron, we do considerably better. Now, if the flows are only 800 C, the gain is a factor of 4. If you go up to 1600, it's huge, it's 66. And so for the more typical flows, 1200 C or so, it's around 30, let's say an order of magnitude for that. So this motivated an effort on my side to determine whether hot flows this large actually occurred on Earth, and what this might imply for lava flows on Venus. So going to the literature, the only thing I was able to find on the subject of the rate of volcanic activity on Venus was a paper by Byrne and Krishnamurthy in 2022. Now they were interested at that time with seismoacoustic observations, something I was also interested in. Balloon missions last about 60 days, so that was their interest window. And they anticipated in a 60-day window, you get maybe 4 new eruptions. Most are relatively short-lived. Within the 60-day window, 20 eruptions are projected. But it turned out that none of this was really relevant because they didn't include any estimates of the size of the flow, which we need to know to determine the probability of orbital detection, or the temperature. So I really had to look elsewhere. And I found, and before doing that, I try to understand a little bit more about what's going on with lava flows and cooling. So it turns out that hot lava cools very rapidly by radiation to the environment. At least that's when there's clear skies. And you see some pictures of this illustrating this. So on the upper left is a picture of a Pahoehoe flow cooling as it squeezes out from the vent. So you can see it's only very close to the vent that the flow is glowing red. And it's cooled very quickly so that near the end of the lobe, it's no longer visible as optical emission. You get similar things for different reasons with our flows, where the fracturing of the flow causes underlying hot lava to be exposed. And then on the lower left, where you have a spray, that cools even more rapidly because it can cool in all 3 dimensions. And you see here a spray of ash particles, and you can see they stop glowing in some cases before they even reach the top of the parabola that they're launched upon. So clearly this process on the Earth can be quite rapid. And then, of course, the area of exposed lava will depend on the volumetric rate of eruption. If you only have a very slow rate of eruption, you're not going to have much hot lava around. So it really does hinge on a very active eruption regime. I took a look at that, and I put together some numbers to set some upper limits to what you might experience here. So if you just equate the energy supplied by sensible heat of cooling and latent heat of solidification to that lost by radiation, you can arrive at a limit to the maximum area of hot flow, and that's going to be proportional to the effusion rate and inversely to the effective emissivity. So you see here that if the effusion rate is about a meter cubed per second, then the absolute maximum flow you'd be able to see would be a few times 10 to the minus 3 kilometers squared. But if you get up to 100 meter cubed per second, then you're getting a significant fraction of a square kilometer. But under no circumstances are you going to get, tens of kilometers squared. This is all done for like a 1200 C lava flow. Now on Venus, it turns out things are a little more favorable because a lava flow cools in a few minutes. On Venus, it's said to project to take as much as 30 times as long, according to a recent publication by Ganesh et al. At the LPSC. I'm a little skeptical it could be that good, and but I haven't yet delved into what the numbers might be. But at least I took an order of magnitude here, and so here then on Venus, a flow of the same effusion rate as on Earth would have a much greater area and would correspondingly be easier to detect. So then let's look at some of the actual data. So a paper by Nadud-Vari et al. In remote sensing in August of 2020 looked at this and they actually mapped out using Landsat data the area by temperature, and they were looking here at 30 meter square pixels. And I didn't have access or an opportunity to look at the original raw data, so I just looked at their publications and counted up pixels. There are not very many of them here, so it was not a very time-consuming task. And I did that for a eruption at Kilauea in July 2018, a very large eruption, and another one for Holaran in Iceland 4 years earlier. And from that, just looking at the red and orange areas in the picture on the left, I was able to determine that there was about 0.11 kilometers squared at 860 C and 0.25 kilometers squared at 800 C. Now, you'll notice here that these numbers are quite a bit smaller than the eruption temperature of 1200 C. So what actually you're seeing in here is these areas are not completely covered by this very hot lava. There's just a portion of the area. So what you're seeing here is in effect a brightness temperature for those regions. So in the case of Holaran, there does seem to be a bigger portion of the area occupied by hot lava here. And so here we had something like 0.047 kilometers squared at a temperature of 1020 C. There were some much smaller events I looked at also. Stromboli is of interest because it's been almost continuously active, unlike some of the other volcanoes, with frequent small explosions. And this one was only around 696 was the hottest area here, very small areas here. And the Halimama lava lake at Kilauea was comparable. I concluded at this point that we really needed some more work on these terrestrial analog, and Paul Byrne has agreed to collaborate on this, and we're just starting to get going on actually looking at raw Landsat data and analyzing it in a way that's best suited to the problem at hand, and probably extending that to the other features too. But I worked with what I had here. But before doing so, I also took a look at EO because some very similar data had been collected on EO back after the Galileo encounters in 1997. So on the left, you have data from the solid state imaging system. This was not a close flyby by any means. It was when EO was in eclipse. So you're seeing no solar illumination on EO this point, and the image on the right is 7.6 kilometers per pixel, the solid state imaging system. On the left, on the right, we've got the Galileo FIMS, 362 kilometers per pixel, much worse than on Venus, by the way. And you can see here that we're getting strong signals. This is interpreted to be 1550 C from the solid state imaging system. And if you take that temperature, you get an area of 0.03 kilometers squared. And then the NIMS data was broken out based on the fact that there were several different bands they could look at into areas at different temperatures. I should say, my belief, these are non-unique, and this doesn't exclude the possibility that the temperatures on EO were not as high as 1550. I think it's just one interpretation. So with that, I was ready to make the comparison between the observations and the theory. And this is what it looks like. So you can see, first of all, the EO. If EO were on the surface of Venus, if the Pele and Pallada were on the surface of Venus, you'd have no problem whatsoever with detecting that. You wouldn't need to go to 0.7 micron either. You could see it at 1 micron and the window at 1.18. I didn't indicate which the windows were. You can't continuously see this at all wavelengths, but there are windows across this band. But among the Earth analog candidates, only the Icelandic candidate, Holoran, met the threshold criterion here. Kilauea didn't actually get there, although, you know, I think I only looked at a portion of the event, and it's possible if we looked at different events at different times, there were times when that eruption would have met the criteria. The lake and Stromboli were far too small to be detected. So, so this is the case, however, if the emission were at the same level as on Kilauea. I then asked the question, well, what if the eruption rate's the same, but the radiance of heat from these events was suppressed by the Venusian atmosphere? And this is what you see in this case. You get the area of emission increased by about a factor of 10. And so now for the larger events, Holoran and Kilauea flank eruption, you move into the detection range, so you're even able to see these at 1 micron. So that's pretty convincing. You can do this in the 0.7 or 0.75 micron window. Another possibility is that these eruptions on Venus are at much higher temperature. This is This is a possibility looked at here. So I've assumed that they're 200 degrees hotter than on Earth because of high magnesium content. Now, terrestrial comatite flows have erupted as high as 1600 degrees. It's 400 degrees hotter, but I just took a more modest look at this. And you can see this also would move us into the detectable range. But Kilauea and Stromboli, I think, are still going to be undetectable. So the conclusion is if flows on Venus have this same volumetric eruption rates as major terrestrial flows and erupted at higher temperatures, they would be detectable. I think it doesn't show here that they'd get into the 1.0 micron, but certainly in the 0.7 micron range. I didn't actually combine radiation blocking and higher temperature, but you can imagine here that would lead to even bigger signals if that were the case. So then what does this imply for actual observations? So that's the next important thing to come to grips with. So what I looked at here, first of all, was the temporal evolution of these events. You know, if they occurred for only a very short time, or they were occurring continually, it would be very difficult to detect the changes we're talking about. So I looked at what the history of Kilauea and the Haliran options were, and they were quite different in character. Kilauea rose to a maximum level and stayed at that level for a while, and then dropped away. And then Haliran was very intense initially, and then sort of ebbed away on like an exponential kind of pattern. So the question then is, well, how would this square with detection? Well, the first thing you have to recognize is that the Venus day is very long, the solar day here. And so you have nighttime when you can make the observations, and then an interval of 58 days where nothing is possible before you have another night where you can make observations. So, then the question was, well, how does this tally with what kind of missions we have? Well, we have two missions that are planned, both of which Darby Dyer is involved in and is a member of the instrument teams that can make the relevant observations from both Veritas and Envision. Both are equipped with a near-infrared night-side imaging capability. It's a very similar instrument, maybe identical. It has a different name. So this could be potentially done from Veritas and Envision. The orbit of both is very similar, near circular, and both are near polar. And both have periods of about 96, 95 minutes. The ground track is about a kilometer per second. But as you'll see shortly, because of very slow rotation of Venus, they don't observe the same place on the planet very frequently. Another approach is through a near equatorial orbiter. And there was a mission of this kind studied to look at seismic detection back in 2018 called VAMOS, and it's pictured here. And then I was involved with a mission concept to the ESA F3 mission back last year, and it was called VIVA, and that had some very similar characteristics, and we actually we proposed to include volcano imaging in that mission. So how would both of these deal with the question of detecting these events? Now, both have circular orbits, which is nice because they enable the surface to be observed at a constant spatial resolution, which is really useful if you're trying to do change detection. Now, here is the equatorial orbit. I've looked at that first. So it's able to observe for most of the nighttime but only to near equatorial latitudes. About 34% for the orbit we looked at, 34% of the entire planet we can look at in this fashion. And so it has very long observational times. Now, for the particular orbit we looked at, which was, I think, about the same, about 3/4 of the altitude was about 3/4 of Venus diameter, that the green area, the spacecraft is not exposed to direct sunlight. It's looking at the dark side of Venus and not exposed to sunlight. In the yellow, the spacecraft is exposed to sunlight, which means to cut down scattered light, you need to have a more sophisticated imaging system. So that's a significant difference. But you can still see you have significant observation time. Now here with the near polar orbit, the problem here is because of Venus's slow rotation time, you see this very infrequently. You'll see it just for a few orbits of Venus until it moves out of range. It moves by about 10 kilometers each orbit. And then it comes back about, I think, 116 days later. On one occasion, it's on the ascending node. On the other occasion, it's on the descending node. But still, observations would be possible in both cases. So we have a trade study for equatorial orbits in process, but you can see here the essential difference between the two kinds of opportunity. So in conclusion here to this session where we're talking about detection from orbit, we can detect events from orbit provided the area of lava emitting near IR is large enough and hot enough. And the night side observations near 0.75 microns seem to be optimal. So the volcanic events on Venus large enough for detection are plausible. We have these large terrestrial eruptions were selected as analog. The observed near IR signals are marginal for detection for Holoran, but if we predict signals after accounting for radiation blocking, they're likely detectable, and we still need to check that out and see that those models are really valid. If eruption temperatures are much higher, this also improves detectability. And so I'm working with Paul Byrne at Washington to continue to explore this possibility. So then we have what kind of a mission would detect these events. Polar orbiter provide global coverage. You can actually look at the entire planet, but you really cannot follow the time evolution of events, and you just have a few opportunities to make these detections. But it is possible and something we should be doing. It may be better to try and do this with the radar events, radar detection, radar change detection, but this is certainly a corroborative approach. The near equatorial orbiters can make repeated observations of near equatorial latitudes. Volcano detection was a prime goal for the ESA F3 mission, VIVA, but that was not selected. But I think a very small mission dedicated to volcano detection and monitoring seems feasible. Even smaller than the F3 mission, which was designed also to the seismic detection, which was much more demanding. I'm now going to move on to the question of what you could do if you could get below these clouds, which interfere so dramatically with detection of volcanic events. So the first question I'll ask is imaging of the surface even possible from below the clouds? And by that I mean high resolution imaging. Do you get away from this scattering phenomena? And then what kind of platform could make this feasible? What might the images look like based on terrestrial experience? What might we see? And what technology can enable a really long duration atmospheric platform? I'll then look beyond the science of volcanoes to talk briefly about the other kinds of science such a mission could do, and then how PSI is involved in defining the science and developing the technology. So going back coincidentally, it was about 25 years ago that Vasily Moroz talked about imaging the surface from below the clouds at the same time as his colleagues in Japan were looking at the problem of detection from observing volcanoes from above the clouds. And he concluded that the major challenge was Rayleigh scattering from the thick, dense atmosphere. He concluded that to do daytime imaging, it would only be possible at a distance of less than 10 kilometers from the surface because of the background of Rayleigh scattered light. And that's why Da Vinci, which is going to descend on the day side, it's probably not going to be able to see very much until it gets down to altitudes like that. And so nighttime imaging, on the other hand, should be possible from below the clouds, but surface contrast would be attenuated by Rayleigh scattering, as well as some subcloud haze, of which the nature is somewhat under debate, and what produces different results depending on how dense it is. So this potential of obtaining images from a balloon platform operating below the clouds spurred considerable interest in updating Moroz's analysis. And this is what we did back in 3 or 4 years ago, finally published in 2024. And this effort was led by Anthony Davis at JPL, who is a real expert on this, did most of the work in connection with terrestrial clouds, was able to apply this to Venus. I'm not going to describe the means in which he did this. I don't really understand it very well, and it's been a while since I refreshed my mind on it, but it was a radiative transport problem, and he did this not just for 1.02 micron as the analysis of Moroz was, but also did it for other wavelengths. It used a custom backward Monte Carlo model, and this was developed because this is well suited for a situation where the sensor is actually inside the medium in order to introduce the inherent numerical noise. And the analysis was done for only ambient surface emission, but the potential of imaging hot flows can be easily inferred. In fact, it works so much better when the flow is much hotter than the surrounds. So, subcloud imaging, what were the findings of that? Well, the findings that you can do subcloud surface imaging at about 10 meters per pixel, but with loss of contrast in the imaging. And the sources of contrast lost are Rayleigh scattering, haze particles, and motion of the imaging platform, because the emission light levels are quite low, and the vehicle is moving. If it's in the cloud layer, it's moving at the speed of the cloud, around 60, 70 meters per second, and so you're having to deal with that to take the imaging. So the conclusion was that the best wavelength to look at was 1.18 micron, and direct photons there constitute around 50% of the radiation. 0.85, which is good for the above the cloud imaging, you only have 7.7%, so that's not good at all. And 1.01 micron is somewhere in between. So this motivated us to really look pretty seriously at this. And one of the earliest efforts here was to look at a vehicle that would actually descend below the clouds. And we had a paper that was included in the decadal survey paper that described this concept, and we were able to get funding for an SBIR program to pursue that in the following 3 years. And this shows the results of that. A balloon capable of operating at as high as 134 degrees Celsius was tested for 4 hours, where it was pressurized to 11.5 kilopascals, and 45 minutes at 15 kilopascals, which are way above the levels needed to implement a mission implementing the altitude control approach shown. This is a multi-segment device. We only tested one segment at very high temperatures, but flew a multi-segment balloon in the free atmosphere and demonstrated that it would descend and ascend under control. And then finally, the thermal control of this involved testing in the laboratory in a thermal chamber, taking the temperature up to 134 C for 4 hours and being able to hold the temperature of the components in the gondola at ambient temperature. So that convinced us of the feasibility of doing this. But better approaches seem to emerge here, which would involve not taking the temperature, taking the balloon itself down. And these involve deploying a multi-kilometer tether, attaching a payload to that, which would be optimized just for operating the thermal imaging. And so this is the subject of a current phase 1 NIAC study led by Ben Hockman, a roboticist at JPL. So what might we see if we were able to get below the clouds and achieve this kind of resolution? So what we've done here is we've looked at satellite pictures that are features that are relevant to the Venus case. Venus is very much a volcanic planet, and so this is what I think we might be able to see. Now, some observations based on just the resolution we have, 100 kilometers, by Seuss Makar have led to a conclusion that fresh lava flows on Venus will have higher emissivity. And presumably that the older the flow gets, the more it will approach the emissivity of the average surface. So similar effects occur on Earth, probably for different weathering reasons. But you see here the very dark features on the upper left are the freshest flows, and then the gray-looking flows are flows that occurred earlier. And then over on the right, you can see an actual current flow against some of these older flows, showing that we might be able to, if we're lucky, observe a feature where there's an actual active flow at the same time as we're seeing the older flows. Now, we're not going to do this with exactly the same sensor. As I mentioned earlier, if you're doing this at 0.75 microns for the hot flows, it's like 10 to the 6 times as high as the emission from the ambient surface. The ambient surface, you're probably not going to look at these low wavelengths anyway, but I think you get the picture. So we can also see probably variability in the hot flows, as you see in the lower left. And then another possibility that was pointed out when we did the paper for the decadal was that you can not only image the surface, you can also image gas, as was done here with SO2. Now, will you see SO2 emitted from a volcano at Venus? Well, probably it's going to be concentrated enough. You're going to be able to see a signal, but maybe H2O might be a better target. So we're pretty convinced you would see something from this mission. So how are we actually going to do this? What we want to do is to get a long duration mission. And the kinds of balloons we've been developing so far is this one, which was tested about 3 years ago now in the desert in Nevada, have a lifetime of 3 months, and we want to operate for much longer than that. So the approach we're taking here is something that can only be done at Venus. It could be done at Mars too, but not on the Earth. And that is to electrolyze the atmosphere. And so when helium leaks out, we replace it with carbon monoxide and oxygen, which are lower molecular weight gases and would also produce lift. Not as good as helium, but nevertheless good enough to keep the balloon sustained. This is done with an electrolytic cell derived from the MOXIE experiment that's developed by a company called Oxyon in Salt Lake City. In fact, I was just up there a couple of weeks ago where I took this picture and they told me in detail about how this worked. And it's a very impressive piece of technology. And we have a phase 1 study that's just been completed, led by Dr. Mike Hecht. JPL was participating in that, and I was involved in that too at that time. So where does that lead now? Well, phase 2 of NIAC, Mike has led this proposal now out of PSI, and I'm involved with this activity too, and I'll tell you now a little bit about what's involved. I think we have just 2 or 3 minutes to leave some time for questions. So we're looking at a mission here called BEAVER. Now everybody, when they coin an acronym, like to have an acronym that has some other meaning, and apparently BEAVER is an MIT one of their preferred terms. I'm not quite sure what it means there, but anyway, that's what BEAVER is: balloon exploration of the atmosphere of Venus with electrolytic replenishment. So we're looking at a 10-year lifetime mission here, enabled by this EVE technology. We're also looking at what we can do if we deploy beneath the clouds. It would be needed for the science we've been talking about here, but not for everything. So the science team is going to look at a range of things. Darby is going to be interested, of course, in the compositional mapping. Now, for Veritas and Envision, she's going to be limited by the resolution loss. In this case, she's going to be able to see the entire planet, 10 meters, 50% of the planet, we believe, with pretty high contrast resolution imaging. Kirby Runyon is involved in this too, and he's interested in the geology. Paul Byrne is interested in the geophysics and the volcanology. What we can do as we develop ground tracks across the planet over the 4 to 10-year lifetime, we can detect remnant magnetism, and we can also do gravity measurements, we believe. It's something that we're going to be looking at carefully. It's not something that has been talked about for any simpler mission, but we believe that we have the capability to fly a sophisticated gravimeter on this mission. Siddharth Krishnamurthy is going to be looking at infrasound. There are various ideas for how we can enhance infrasound measurements for seismic observation beyond what has been conceived before. James Lyons has been involved in this, and he's interested in atmospheric chemistry. I've been working with James separately on some ideas for doing aerosol ground measurements at the JPL Planetary Cloud and Astrobiology Research Facility, Cloud and Aerosol Research Facility. But James has some very interesting ideas, mostly applied to early Earth, but well applicable to Venus. And David Grinspoon, who's joined PSI following his departure from his astrobiology senior leadership position at NASA headquarters. David has been interested in life in the Venus clouds for some time, and we're going to engage him in a serious look at what we can do with this mission. And I'm involved in putting together what we're calling a science mission and technology roadmap for this. So, in summary, the thick atmosphere and cloud layer on our sister planet presents both challenges and opportunities for science. Detection of active volcanism from orbit appears feasible if rates of effusion are as large as occur at active hotspots on Earth. Observations with Veritas and Envision are possible, but we do have the challenge of long periods. Equatorial orbits look a little more promising for superior temporal coverage, but we need further work on that. To really get an understanding of the morphology of volcanic events, we need to get below the surface for long durations. And PSI is proposing further development of this solid oxide electrolysis technology that may enable capable balloon platforms, and we're looking at the science that we can do, which is no longer limited by helium loss. Thank you. I think we have a little time for questions.
That's wonderful, Jim. Lots of really great and interesting stuff there. Thank you so much. And we do have time for some questions and comments. So speak up, everybody, on all this cool stuff. I'm trying to, oh, there we go. Who has questions for Jim? Hey, Paul Byrne is there. Great. I'm glad to see you, Paul. Welcome. I'll call on you. Oh, Vicky's got her hand up. Let's go to Vicky, and then we'll go to Paul.
Really nice talk, James. Thank you so much. Learned a lot. I have one quick question about the temperature. Is it absolute temperature? Are we looking at delta temperature? And just considering that the delta temperature is so much smaller on Venus, even for a high temperature lava flow, than it is on Earth, how does that figure in to things?
Well, the temperatures I cited were all temperatures in degrees C, and I wasn't presenting deltas. I think except for the very first chart where I showed the Hashimoto results, which were in delta temperatures. Now, of course, the delta temperatures on Venus relative to the background are going to be lower than on Earth. So I took that into account in the analysis. One thing that I still need to sort of flesh out a little bit is that when you compare the likelihood of volcanic events on Venus and on Earth, you sort of say, well, they're very similar planets. They have a similar amount of radioisotopic materials, but on Venus, things have already been superheated to the average temperature 460 C. So that radioactive material doesn't have to do as much work to get it to eruption temperatures. So there are things like that. But did I answer your question?
I think so, except that so when we looked at temperature, I'm sorry, I didn't mean absolute temperature as in degrees K, but temperature it's not relative to the delta temperature, because I would think that it's much easier to see a high temperature when it's against a very low temperature background. But I don't understand the whole process enough to say that. So that's why I'm asking, is there, if a flow is 800 degrees, round numbers on Venus, that's just a delta temperature difference of 300, whereas obviously for Earth, it's closer to 800 degrees.
Right. That's what makes it so hard on Venus, that you have the background. Yeah.
Okay, so this is all, you've got that.
That's all taken into account. Yeah.
Okay, thank you.
Yeah. And that's why when you go to the low wavelengths, then the signals from Venus are much lower than they are at, say, at 1 micron, because of the shape of the curve here. If I go back to the very beginning here. You see here that the emission from Venus, the 460 at 0.7, is orders of magnitude lower than at 1 micron. 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 1 micron.
Thank you.
Okay, Mike Hecht.
No, I was just going to add to that. It was the same thing I put in the chat that in terms of radiation, it's going to go as t to the fourth. So, well, of course, in terms of what you observe, it doesn't really matter what the background is, but so much. But in terms of cooling, he said it goes as t to the fourth. So I don't think the t0 to the fourth associated with the background is that important even on Venus, and because it's such a strong function. But I think in terms of cooling rate, presumably what is important is the convection in the atmosphere. And, I'm saying that only because the atmosphere is, 90 times thicker than on Earth, and the temperature in Kelvin is only, two to three times higher. So on balance, I would think it would cool faster from convection.
Well,
Radiative cooling would be about the same. Is that right?
Well, there were a series of papers on this, and the first one, and I can't I can send these to you. I can't recall the name. Made exactly this point: convection will be better on Venus, and it was a paper that was really analyzing behavior on the Earth. But then there was a second paper by somebody at Rand Corporation in Santa Monica here, which was kind of interesting, who didn't seem to do any other work, who said, hey, you guys forgot the radiative situation on Venus. And he demonstrated that was produced a dominant effect, and it would and what would happen is that the atmosphere would heat up and radiate back and suppress things. My sense is that all this is going to depend on how long the event lasts, because there's so much mass in the atmosphere. So I think I need to understand that problem a little better. The recent paper in 2024 said that a lava flow on Earth cools in a few minutes. On Venus, it would be 90 minutes. I'm not convinced it's going to be that big a change, but it will be longer.
Thanks.
Let's see. One thing I wanted to point out is a couple of things about PSI, because we've got a number of Venusians here, which is great. We had not formally set up a Venus research cluster at PSI, but we did set up an email group, and we can provide more resources like a web page and so forth for you all to collaborate on ideas. And I saw that I think David Grinspoon sent out a test message, which is great. And we're happy to, get that going. And so if you find that you need resources, let me know. We had kind of more formally set up research clusters for like the Moon and Mars, but I was kind of waiting so far on Venus, but I know that there's a lot of interest and activity, so I go for it whenever you want. The other thing I want to mention is the retreat's coming up next month. And I know that there's a number of Venusians here on the call. We haven't heard from you one way or another about whether you're coming, but it's a great opportunity. I hope you can come, and it's a great opportunity for FaceTime and collaboration together. We can have a Venus breakout or an Eve breakout or whatever you want. It's up to you. So
I would have liked to come, but I had a prior commitment. A family vacation is all scheduled, and so I won't be able to be there those days. So
Same here.
Thanks, Jim.
Yeah.
Who else just said same here?
It was Mike Hecht.
Okay, so I don't think we've received your formal RSVP. So let me just relay those to Kim and make sure that we get you down, and then we'll quit bugging you. But anyway, think about the research cluster too, because
I think that I'd be interested in doing something like that, and getting more people involved. We have Kirby's involved in this right now, and I saw Larry Lebowski earlier, who I worked with many years ago. I see Alan Howard there now. Alan, hello. It's been a while.
So it looks like Larry had to drop off,
Yeah,
but
he told me he had to drop off.
okay, okay,
Yeah.
great. Um, well, it's fun to get the band back together, Jim. Thanks for doing the talk, and
Yeah,
this is really interesting.
one thing that Mike mentioned here, you know,
Okay.
I just touched briefly on beaver. It's the mascot. That was the word I was struggling for. It's the MIT
Yep,
mascot. I'm
yep.
sorry. And and so he was suggesting maybe we should give a pitch on that, which does you know full justice to the technology and what we're grappling with right there, and talk about some of the other science. And if Paul can join us, Paul has been very active for looking at a precursor mission too.
Yep, and I think that, for any sort of PSI focus group or anything, I think it's perfectly fine. You know, it's up to the members
Yeah.
to have kind of external folks involved. I think normally that's completely fine. So it's up to you. Okay. We're gonna wrap it up here. Thanks again, Jim. We'll stop the recording, and thank you again for an excellent talk.
Okay. Well, thank you for the chance to talk here, and I've enjoyed getting this ready and sharing
Great.
this with some of the other people here. Very good. Thank you.